Yeah, thank you very much, Alexander, and thanks for inviting me here to give the talk about graphene oxide composites for medical and agrochemical uses. So the first question is, why do we use graphene oxide actually? The rationale is to use more to design more tools for drug delivery. So that's the idea. So the box is still not full. Drug delivery in terms of cancer treatment, in terms of agrochemical applications. We have tools, but the toolbox is not definitely not filled. And the idea is to fill it with more and better tools. That's the rationale behind that. Okay, first look on the two slides we submitted with our proposal in 2019 when we applied for the LIT money here, so to speak. So that was what we described, the delivery and controlled release with new biocompatible and biodegradable matrices. In this case, our idea, our hypothesis, Dr. Perez is sitting here. He did a lot of details in this research. So we thought, why not going for graphene oxide as a base? And the idea is then, of course, to add new tools to this toolbox, as I said, based on graphene oxide for drug delivery and controlled release applications. And our first idea was to create, based on graphene oxide, so a derivative of graphene, based on that, to create a composite system with polymers and drugs and so on for treatment of cancer and also for helping plants to grow. So that was the general idea, linking in this project, a 2-year project, the graphene oxide, abbreviated GO, with polymers for better biocompatibility and encapsulating or even linking drugs to that material or composite as well. And then, of course, trying to find out how they will be released, these kind of drugs in or in combination, in contact with cells and tissues and plants. That was the idea. So first of all, we should have a very brief look back to graphene. What is graphene? Graphene is a 2D layer system. Actually, one can obtain it from graphite, but it's only a 1-layer system, a 2D layer system based on hexagonal carbon atom rings, and of course with a pi conjugated structure. It's showing different properties. Conductivity is very important, strength, stability, chemical stability, which could a very interesting topic in drug delivery. It's not always about fast degradability. Sometimes we need longer survival of the carrier system. We wanted to use this as a base for carriers. But the big problem is it's too hydrophobic and toxic for biomedical applications, the pure graphene. It's expensive and hard to get, and yeah, that causes, of course, or asks for alternatives. And an alternative would be to use graphene oxide. It is just the oxidized form, if you like, with a lot of carboxy functionalities. Main topic is, of course, we have oxygen in the system, epoxy functionalities, hydroxys, carboxys, so acidic functionalities, which we can use as anchors for polymers and for drugs. That was the idea. So we see graphene oxide as a platform, has certain advantages. Again, similar effects like graphene itself. It's amphiphilic now, not so much hydrophobic as graphene, because we have hydrophilic groups which can interact with living tissues, surrounding aqueous systems and so on. It is less toxic than graphene, but still not biocompatible. So the idea was to use these kind of functionalities and then link it to more biocompatible groups, polymers, and so on. So the idea is, as I said, to create more tools for a better filled toolbox, so to speak. Or in other words, graphene as the base, red light, too toxic. Graphene oxide, okay, not very biocompatible, but at least showing these kind of chemical functionalities in order to introduce polymers for better biocompatibility. Yellow light. And green light only when that was our hypothesis in the beginning, when writing the proposal, when linking that to polymers, of course biocompatible polymers like here chitosan, or in this case it's glycolated chitosan, and of course the drug. Then we have green light. That was our idea, and of course now it comes to all the experiments we performed. So what drugs did we focus on? CPT, camptothecin, was one, which is a natural anti-cancer drug and can also be synthesized in the lab, of course, but that was not our goal. We just bought it and linked it to the polymers and the graphene oxide, or via graphene oxides to polymers, so to speak. It shows a very good in vitro cytotoxicity, but major drawbacks of these typical anti-cancer drugs, their low aqueous solubility and side effects when applied in pure form. Chemotherapy with these pure substances is very much linked to side effects. So why not using that with a carrier system, which always has certain advantages, keeping it more in a controlled way, the whole therapy, anti-cancer therapy, and the carrier often is showing a very strict transport towards the tumor, and that's also helping by the help of the polymer, so to speak. As a parallel project, as I said, plant growth was our aim with other drugs, these so-called brassinosteroid analogs. They are also natural components, natural or plant hormones actually, and they can be used for enhancing the growth of plants. So they might increase crop yields up to 30%. Also here we have low aqueous solubility. Why not including polymers with a GO, graphene oxide platform? So the task was, first of all, in these 2 years to obtain graphene oxide, either using graphite flakes as a base or renewable biomass waste, then prepare the composites with polymers, link that to drugs, and then of course assess cytotoxicity, cell uptake, and the agrochemical activity. So very first look or short look on the fabrication of graphene oxide. We used these flakes, so that was graphite actually, and treated that via the in the literature described hammer method with severe chemicals, sulfuric acid, sodium nitrate, potassium permanganate, and so on, hydrogen peroxide. And then in the end, got a yield of 56% graphene oxide. And of course, we wanted to, first of all, create a dispersion. We sonicated that, and only after tip sonication, we found out that we got nanoparticles. Before, with only simple sonication, it led to aggregates, micrometer-sized, 200 nanometer-sized, much tinier fragments or particles we obtained after this tip sonication. We also thought, why not buying it? Why making it? So we bought, that's available with Sigma, a chemical seller, so to speak, graphene oxide. But we found out, for example, by using infrared spectroscopy, that the typical signs or indicators for carbon or carbonyl functionalities, carboxy functionalities, which we wanted, because that's our anchor groups for linking that to polymers and drugs, are not as present. This is the commercial product as in the one we made by ourselves. So we didn't do a lot, I'm not presenting any results of this GO from Sigma. And in the elemental analysis, we also found out that the oxygen content was much lower. We wanted high oxygen content. So this is CHO, oxygen, the last number here in our own made, homemade, so to speak, lab-made GO showed higher oxygen content, which we wanted for the immobilization of polymers and drugs. And by the way, we found out that these aggregates were much, much larger, maybe for drug delivery not appropriate. So we didn't, I'm not showing any results of this commercial one. GO can be synthesized by using renewable resources. So Mr. Perez, he brought from his home country, Cuba, these sugarcane fibers, bagasse. So these are the residues of actually fabrication of drinks from sugarcane. And he, of course, heated it, dried it first of all, and then ground it with a coffee grinder. That led to this powder here. And in the next step, it was or underwent a pyrolysis. First of all, 250 degrees, 4 hours. That's telling us the yield is higher, or told us in the result, but it contains still some fiber residues. But at much higher temperatures, shorter times, we observed less yield, but much better and more fine powders, so to speak. So we lost all these fibers. And in the end, again, a short look on the carbonyl functionalities. They also here show us that we have enough carboxy functionalities, not to going too much into detail. Before we added then the polymers and the drugs, which was the actual concept, we pre-functionalized it. For example, these so-called epoxy groups were chemically treated to open them up, these triangular structures, obtaining more anchor groups for polymers and drugs. And then again, seeing that the number of oxygen was even increased. Okay, so next step was, of course, introduction of the polymer, linking the graphene oxide to polymers. Here, chitosan, or a so-called glycolated chitosan, and the drug, here in short, CPT. We have already seen camptothecin, the anti-cancer drug. And we found out the so-called zeta potential also considerably changed from minus values to positive values, telling us that the actual negatively charged carboxy groups were transferred into ester functionalities linked with the camptothecin. And also the surface area, this is specific surface area after immobilization of polymer and drug, CPT, was considerably lower because of consumption of the coverage of this surface, so to speak. In the end, we obtained up to 2% loading with the anti-cancer drug, the GO content up to 13%, and around 85 to 98% polymers. So what did we do? First of all, of course, having a short look on the release effects. Yes, that occurs. We can release the CPT, our camptothecin, from the composite material, and that occurs here faster when, for example, using a chitosan as a polymer, as a additive, so to speak, linked to the GO. With PEC, it's slowed down, so to speak. So another option of increasing the number of tools in our toolbox, having a certain time where we release these drugs. First thing is, of course, or was then having a short look on human blood cells, because if this composite material is then to be applied in the human organism, it should not kill blood cells, of course. And we found out the pure GO is still toxic. So the red columns here shows hemolysis, and that's, of course, not what we are aiming on. We want to protect human blood cells. And the pure drug also leads to this kind of lysis of these blood cells. But with the composites here, GO, GC, CPT, again, graphene oxide, the polymer and the CPT, we have received even negative values, so meaning that the blood cells survived. And then further tests about the toxicity of these GO first of all, the linked or the graphene oxide with the polymers, and we see here in these tests viability versus concentration, and we see that the actual graphene oxide in its pure form is still a bit toxic, so the viability is not so high, maybe reaching a bit like 50%, but higher viabilities, survival, in other words, of the cells when using the graphene oxide together with polymers. But here still without having a look on the drugs itself. And we had a look on not only keratinocytes, but also human breast cancer cells. That was shown here. The polymers helped to let these cells to survive with graphene oxide. You might ask, why surviving? This is only showing that with the polymers, the graphene oxide is less toxic. The cells survive. Now, of course, adding these anti-cancer drugs, CPT, for example. And we found out, these columns show us here the viability that goes down. Of course, with the drug, we want to kill the cancer cells. The higher the content, the better the effect. So the viability goes down only now after applying the whole composite, not only with the polymer, but now with the drug. And that helps to reduce the actual survival rate or viability of these cancer cells, exactly what we wanted, treating the cancer cells. And that it seems to be more efficient than using the pure non-linked CPT in its pure form, so to speak. So significantly superior toxicity when using these kind of composites with polymers, GO as a base, as I said, and not using that or in comparison with the pure CPT. We also had a short look on the cells. Is the composite material really internalized? Yes, just recent experiments proved us that they are internalized in these cancer cells, and they are causing cell death, exactly what we were aiming on. And now, just briefly on the second application, so the agrochemicals we are using, in this case, same platform, GO with a lot of carboxy functionalities after opening epoxies and so on. Adding then another polymer, here as an example again, chitosan, which is of course a biopolymer stemming from chitin. You probably heard about that, which is a very important part of crustaceans' skin, so to speak, or constituent of that. And then linking that with one of these brassinosteroids as an agrochemical substance. We found out, or did similar experiments, finding out that we actually immobilized that drug on the surface, not going too much into detail. Loading was here not reaching 1%, but maybe sufficient for an effect, for an agrochemical effect. First thing again, do we have some kind of cytotoxicity? Here we don't want any cytotoxicity because of the, in this case, application agrochemicals here for better plant growth, for using that as a fertilizer, so to speak. So here it seems the whole composite material, graphene oxide, polymer GC, chitosan in other words, and the drug showed a higher viability, nearly reaching 100%, which is quite good. So the keratinocytes, which were investigated, survived quite well. It shows us they are relatively harmless, at least in these kind of composites, where we have the three components, GO, the polymer, and the drug. I'm just wrapping this up. We had a short look on the growth of, in this case, cotyledons from radish, and the plants grew much better, higher concentrations here on the left side, which is different to what we have seen before. Higher concentrations, higher weight gain. That means it works. So the plants grow better, faster. And that leads me to the conclusion. So we, in these 2 years, we created GO by ourselves, not only using commercial graphite, but also renewable resources, which is nowadays, for sustainable reasons, a very important factor. We created composites, different ones with CPT and agrochemicals. We functionalized the GO with polymers, and then, of course, immobilized the drugs. And we investigated that and found out that these, the GO polymer CPT is more toxic to the cancer cells than CPT alone, which is advantageous. And the polymer agrochemicals here are non-toxic to keratinocytes, as I said, but they are showing good plant growth activity. So in both completely different applications, we saw successful usage of this kind of composite system. That leads me to, first of all, of course, thanking the LIT, Johannes Kepler University and LIT for funding, and our collaborators, Dr. Roschka at the Kepler University Hospital, Professor Schwarzinger and Dr. Schwarz here for elemental analysis, Claudia Schmidt in Paderborn, Germany for elemental analysis, and Mrs. Dolberger for AFM imaging. I haven't shown anything of that, but due to time limitations. And finally, thank you very much for listening. Thank you.